Hello viewers, I am Kausalya. Today we are going to solve problem number 10 under the category Routh stability criteria. The problem is the open loop transfer function of a unity feedback control system is given by this expression. By applying the Routh criteria, discuss the stability of the closed loop system as a function of k. Here k is a constant. Determine the value of k which will cause sustained oscillations in the closed loop system. Sustained oscillations will be caused only when we have roots on the imaginary axis. Right. What are the corresponding oscillating frequencies? At what frequencies the system will oscillate? Right. So, here the open loop transfer function is given. So the first step is we have to find the closed loop transfer function. So the closed loop transfer function is given by the expression C of s by R of s is equal to G of s divided by 1 plus G of s into H of s. Here the G of s value is given in the problem. So just substitute the values here. So in the value of H of s will be 1 because it is a unity feedback system. Right. And the next step is we have to take LCM for our denominator part. So taking LCM is nothing but these entire terms will get multiplied with the 1 here, right? So when you take LCM, you see we are having expression like this. The numerator term remains as such here and this denominator term I am just multiplying. So s plus 2 into s plus 4 into s square plus 6s plus 25 plus k and the entire term divided by this denominator part, you see. So here, since both the denominator terms are same, they cancel each other. And finally, we are having an expression as k divided by s plus 2 into s plus 4 into s square plus 6s plus 25 plus k. So this is our closed loop transfer function. So we can tell whether the system is stable or not by examining the characteristic equation, right? What is the characteristic equation here? The denominator part of the closed loop transfer function gives you the characteristic equation, right? So this is our characteristic equation. So we are going to solve this characteristic equation, right? So first I am multiplying these two terms, that is s into s, s square, s into 2, 2s, 4 into s, 4s, 4 into 2, 8, right? And we are writing this term as such plus k equal to 0. Now I am going to multiply these two terms again. You see here s square plus 2s plus 4s is nothing but 6s, right? Plus 8 and this term as such here. Now we are going to multiply these two terms. So when you multiply, you see s square into s square gives s to the power 4 and s square into 6s gives 6s cube and s square into 8 gives 8s square, right? Then move to 6s. So 6s into s square gives 6s cube, 6s into 6s gives 36s square and 6s into 8 gives 48s, right? And the next thing is 25. So 25 into s square gives you 25s square and 25 into 6s gives you 150s and 25 into 8 gives you 200 and this plus k, right, which is equal to 0. So finally I am again simplifying this expression. There is only one s to the power 4 term here. So here I am writing that one. And the next thing is we are combining the s cube terms. So here 6s cube and here 6s cube. So when you add, we will be getting 12s cube. And the next thing is s square. Here 8s square, 36s square and 25s square. So I am adding all these terms and I am getting 69s square. And again we are combining s terms. Here 150s and here 48s. So 198s plus finally the constant terms 200 plus k. Right. So this is our simplified characteristic equation. So from this characteristic equation, by using Routh array, we have to tell whether the system is stable or not. Right. So forming Routh array. Here the maximum power of s is s to the power 4, right? So I start with s to the power 4 here. Since it is an even number, I have to connect all the even powers. So s to the power 4, s square and finally constant terms s to the power 0. And here the second term is s cube. So the next term will be s to the power 1. Here I am connecting all the odd powers. Right. So here I am writing the coefficients. Coefficient of s to the power 4 is 1. and coefficient of s square is 69, and finally the constants are 200 plus k, right? And the next one is s cube. Coefficient of s cube is 12 and coefficient of s is 198. So here I had written 12 and 198. Since we are having bigger number, I am dividing this term by 12 as I am having 12 here. So when I divide, I am having the answer as 1 and 16.5. Right. Next I am going to rewrite this array again. So by rewriting, I am having s power 4 row and this s cube row in simplified form, right? And the next step is finding s square row. The procedure is 1 into 69 minus 16.5 into 1 divided by 1, right? That gives you the answer as 52.5. Here I had written, you see, here I had written the steps, right? So the answer is 52.5 here. And the next one is we are going to find this second element here. So for finding this element, we have to hide this column. Just multiply as usual. 1 into 200 plus k minus 0 into 1 divided by 1. Right. So this is the step. And finally, this gives 200 plus k as answer. Right. And the next step is we have to find s to the power 1. So how to find this s to the power 1? As usual, 52.5 multiplied by 16.5 minus 200 plus k into 1. So here I had written the steps. So when you solve this equation, I am getting the answer as 666.25 minus k divided by 52.5. Right. So here I am writing the values. So when you go for the second term, you see when you hide this, there are no elements here. So we can leave it. And finally finding s to the power 0 value. So here you see this term multiplied with this 200 plus k minus 0 into 52.5 divided by again this corner element. You see here I had written the steps. This multiplied with this. So this one minus 0 into 52.5 is 0. So I had simply written 0 here. Then divided by this corner element. So this is your corner element. So these two terms cancel each other and the remaining answer is 200 plus k. Right. So finally we had formed our Routh array. From the Routh array, we have to check the values of k. Right. We have to find out the range of k for which the system will be stable. So this S0 row consists of 200 plus k, right? So for the system to be stable, there should be no sign change in the first column of Routh array. Right? So in our Routh array, we are having only positive elements. You see, this is our first column, right? So this column has, when you check the previous elements, all are positive here, right? You can leave k, you just check the previous elements, all are with the positive sign. So again, when we make this term positive and this term positive, we can say the system is stable, right? So for that, initially we are considering this 200 plus k. So this 200 plus k should be greater than 0, right? Therefore, k should be greater than, when you move this plus 200 to the right hand side, that becomes minus 200. So the value of k should be greater than minus 200, but the practical values of k starts from 0. So we are considering the value of k should be greater than 0, right? Then the next step is we are moving to s to the power 1 row. So s to the power 1 row has this element, and again this element should be greater than 0. So when you solve, you see, when I move this 52.5 to the right hand side, so 0 into 52.5 gives you 0. So again when you move this minus k to the right hand side, we are having 666.25 greater than k. So what it means, the value of k is less than 666.25. Both they are same. Can you understand? 666.25 is greater than k, or k is less than 666.25. Therefore, the range of k varies from 0 to 666.25. Right? Hope you people understand this one. Yes. Then the next step is they had asked us to find what is the when will be the system having sustained oscillations. That is, to have sustained oscillations, it is mandatory to have row of zeros, right? Again, when you look at the Routh array, here we can make the row of zeros, Right, because whenever you are having row of zeros, we will move to auxiliary equation, and from the auxiliary equation we will be finding the values of frequencies. Right, so in order to find the sustained oscillations, here I am considering this s to the power 1 row. Why I am not considering s to the power 0? Because here when I consider this term, this s to the power 0 row, the previous row contains a constant k. Right. So only I am considering s to the power 1 row. I am making this row as row of zeros so that we can make auxiliary equation easily with this s square row. Right. Here the first term should not contain k. The first element should not contain k. Here even the second element has k, right? So you can ask why we are taking s to the power 1 again. So that is the reason. Right. So to make s to the power 1 row 0, here I have to substitute 666.25, right? That's it. 666.25 minus 666.25 will give you 0. So next we are going for the auxiliary equation. So the auxiliary equation is s to the power 2 row. That is the row which is previous to the row of zeros. Now we had made s to the power 1 row as 0. So what will be the auxiliary equation? This row gives you the auxiliary equation. So how to write? 52.5 s square plus 200 plus k is equal to 0. Right. So this is our auxiliary equation. So when you solve this auxiliary equation, you see we are having only s square terms, the remaining terms are constant, and again here I am substituting the value of k as 666.25. Right. So when you substitute this one and when you solve, you see 52.5 s square is equal to minus 866.25. Again when you divide this term by 52.5, I am having minus 16.5. So here again when you take square root, the final answer is square root of 16.5 is 4.06 and square root of minus 1 is j. So the value of s is plus or minus j 4.06. So when k is 666.25, right, the system has roots on the imaginary axis. That is, when you substitute the value of k as this one, we are making s to the power 1 row as row of zeros. Right. So whenever there are row of zeros, the roots will lie on the imaginary axis. So whenever roots lie on the imaginary axis, the system will oscillate. Right. And finally, we can find out the values of S. So value of S gives you the frequency of oscillation, which is nothing but 4.06 radian per second. Right. Finally, the result has range of K. So this is your range of K for stability. And the system will oscillate when the value of K is exactly equal to 666.25. And finally, the frequency of oscillation is found to be 4.06 radian per second. Right. Hope you people understand the problem. Thank you.